So welcome to this video. Again, we'll talk about continuous functions and we'll see an example of a continuous function and get to know a simple idea that we then investigate and see how far that carries. Okay, so that chapter is titled an example and a warning. And we'll introduce a very simple idea in this chapter. So if we have a multivariate function, let's set up the stage first. Let f x to r, we just consider the reals as the codomain. And again, we'll have x as a subset of r to m, be a multivariate function. What we can then do is we can define something like sections of that function in a certain direction. Let me make a quick sketch to illustrate what I mean here. So let's take the x1, x2 plane here. And you all remember the parabola, the general parabola, f of x1, x2 is x1 squared plus x2 squared. You remember the graph of that one that looked a little like this here, roughly. Yeah, so that was the generalized parabola in higher dimensions. And the idea is now what we can do is, what about we just restrict our variables to one specific direction in the x1, x2 plane. For example, we could choose to restrict ourselves to this direction here, the x2 axis. Yeah, then basically we're cutting through that function with a plane that contains this x2 axis and is perpendicular, so with a plane like this. Yeah, we're cutting through that function with a plane like this. What happens? Basically what we're getting is just a parabola, a one-dimensional parabola in that plane. So we kind of have a one-dimensional section of that function here. And of course we can do that with every possible direction. In this case, the result will always be a parabola because that function is rotation symmetric. So however you rotate that direction, it doesn't change much. Now, the question is, we can do this for every multivariate function, and those sections will then be functions that are defined on the reals and mapped to the reals. So functions that we know how to deal with. So the question is, if we have a look at those sections or that directional functions, and see if those are continuous or differentiable or whatever we want them to be, does this carry over to the higher dimensional function? And we'll investigate that idea here in this little chapter. So let's make this a little more formal. We can define something like directional sections to obtain one-dimensional functions from f. And we'll do this in the following way. We first choose a direction. We call this direction D. And the direction is simply a vector in Rn that is not the 0 vector. So any vector in that x1, x2 plane or in the general x1, 2, xn plane that gives us a direction that's not 0 straight away. And then we consider the line through 0 along this direction. So consider the function fd that results from restricting f to the line in direction D. Okay, so that line would then be 0 plus lambda D, lambda in R. And that function fd would then be defined on the reals, mapped to the reals. And fd of lambda is simply defined as f evaluated on the corresponding point of that line. So we just use 0 plus lambda d. Yeah, we fix the d. We move that parameter lambda along the line, and we'll just evaluate at that point. Yeah, we'll evaluate the function along the line, and this gives us this one-dimensional cross-section fd. And the question is, what can we learn from these cross-sections? If all of these are continuous, shouldn't the function also be continuous? Of course, the reverse is true. If f is continuous, then of course every cross-section must also be continuous. So if f is continuous, then all these directional sections are also continuous. The question is the reverse also true? And the answer is, surprisingly, it's not. So there are examples where all of these directional sections are continuous, but the function still is not. Okay? However, the reverse is not generally true. So even if all fd for all possible directions are continuous, the function f can still be non-continuous. And here's an example to illustrate that claim. So we consider the following function. We define a function on R2 that maps to R. And we'll define that as f of x1, x2 is, usually it will be defined by the expression x1 squared times x2 divided by x1 to the 4th plus x2 to the 2. And of course this definition only holds as long as x is not the origin. Otherwise we cannot define by 0. So if f is if x is the origin, then we simply say the function value is 0. Okay? So that is the definition of the function. And of course, the question is this function continuous at the origin? So what we do is we consider a direction and we consider the directional sections on that function. See if those are continuous. So let's do that first. So let D be in R2, not 0. So that's an arbitrary direction. Okay, then we consider these directional sections here. We consider FD, R to R. Fd of lambda is defined as f of 0 plus lambda d. So, well, 0 plus lambda d, that simply means we have lambda d1 and lambda d2, if d is the vector d1, d2. Okay, well, what is this? In case lambda is 0, then of course we add the origin, so the value will be 0. For lambda not equal to 0, we're in this first case here, so we'll simply substitute lambda d1, lambda d2 into that function. What we get here is, in the numerator, x1 is lambda d1, so we get lambda squared d1 squared, and x2 is lambda d2, so we get lambda squared d1 squared times lambda d2, that is lambda to the third d1 squared d2. And for the denominator, we have x1 to the fourth, so that's lambda to the fourth d1 to the fourth plus x2 to the 2, so that's lambda to the 2 d1 to the 2. Sorry, d2 to the 2, of course. Okay, so that is for lambda not 0, and then we have 0 for lambda equal to 0. Okay, and we can simplify this a little. As you can see here, lambda squared cancels out, so we do just that and get a little simple expression. The 1 lambda remains in the numerator, so we have lambda d1 squared d2, and for the denominator we get lambda squared d1 to the fourth plus d2 squared, again for lambda not equal to 0, and 0 for lambda equal to 0. Okay, so let's see if this yields a continuous function. And we need to make a little case distinction here, depending on the choice of d. So, for example, what we can do is we can make a case distinction on d2 and say we'll first regard the case that d2 is 0, and then we'll regard the case that d2 is not 0. Okay, for d2 equals 0, what we get is fd of lambda is then simply 0, because d1 is not 0. That means the denominator is not 0, because the direction cannot be the 0 vector. But the numerator will be 0. Okay, so the value of that function is then simply 0. And of course, if lambda converges to 0, so we are going to the origin along that line D, then this is going to ft of 0. Okay, So that means for d2 equals 0, we have continuity. For d2 not equal to 0, what do we get then? Again, we want to get lambda to 0. What happens then is that the numerator approaches 0 and the denominator approaches d2 squared. So fd of lambda for lambda to 0 goes to 0 over d2 squared. As d2 is not 0, this is well defined, and it has a value of 0. Okay? And again, all of these are equal to the actual function value at 0. That means fd is continuous on the respective line for all possible directions, for all d in R2 that are not the 0 vector. What about the function f? So my claim was that f itself was not actually a continuous function. And I'll prove that to you. Let me just copy over the definition so that we have an easier time of seeing that. Now, you remember the definition of continuity, which said we need to consider every possible sequence that goes to the point that we're interested in. In this case, that is the origin, 0, 0. So we need to consider every possible sequence that converges to 0. So far, we have only considered convergence of sequences that go along a line. And that's the crucial point here. What about a sequence that does not go along a line? And we will consider such a sequence now. So consider the sequence AK, and we'll define this as 1 over k in the first coordinate and 1 over k squared in the second. For k in n. We will exclude 0 here for obvious reasons. Okay. Then the limit of ak as k goes to infinity, that is obviously 0, 0. So that is a sequence that converges to 0. What about the sequence f of ak? So what we get is f of ak. AK is never equal to 0, so we only need to consider the first case. And then we can just substitute into the function definition. So we get x1 is 1 over k squared times x2, that is 1 over k squared, divided by 1 over k to the fourth plus 1 over k squared squared. Okay, so what do we get? In the numerator, we have 1 over k to the fourth. And in the denominator, we have 1 over k to the fourth plus 1 over k to the fourth, so 2 times 1 over k to the fourth. So this k terms cancel out, and we are left with 1 over 2. Okay, so f is constant along that sequence ak. And of course that means the limit is also going to be 1 over 2. So limit of f of ak is then going to be 1 over 2. And that is not the same as the function value at 0, which is 0. So obviously we have found a function such that the f along the sequence do not converge to the function value at the point 0. So f is not continuous. Okay? So that means the problem here is f may well be continuous along each line, but by definition we are not restricted to lines. By definition we need to consider all possible sequences, and there are sequences that do not go along lines and may behave differently, and that's what happens here. Right? Of course the reverse is true, so if we consider all sequences and everything is fine for all sequences, then especially those along lines will behave nicely. But not the other way around. So be aware that this idea of taking sectional cuts, cross sections of functions, this may take us only so far. At least for continuity, this is a concept that does not generalize that well. We'll still try to apply that concept to differentiability. Again, we'll see it does not generalize. We will need a more general concept of differentiation. But in some cases, this will actually be sufficient. And we'll characterize what these cases are in the next few videos in the coming week. So that's it for today. That's it for this week. Have a nice holiday. Have a nice weekend. And I'll see you next week.